of the Falls of the Ohio State Park. There's a fantastic little movie that shows you the history of the Devonian area that laid down these very flat layers of limestone that were under the shallow sea for a long time. Back when, by the way, Kentucky was in the southern hemisphere. Slid all the way past that kind of where Africa is now. Interesting. Okay, so that's what's happened on Earth, and that's where most of the carbon is. We talk about the carbon, we talk about burning carbon and getting worried about it going up in the atmosphere. Most of the carbon on Earth is locked in the rocks. To do that required liquid water, called aqueous chemistry. And then locked it in the rocks, formed the limestone, and then the biology formed the coral reefs. We've got a lot of carbon. How much? Venus, 90 bars, remember, versus our 1 bar? Venus is carbon dioxide atmosphere. Mars and Venus are the two. Titan and Earth are actually nitrogen atmospheres. Venus has 90 bars. Guess how much carbon dioxide is in our rocks? If we were to release it all, the same amount. If we were to release all the carbon in the carbonate rocks off Earth, just burn all the coal, burn all the oil, and also burn all the coral reefs, get it all out, it would produce a 90-bar CO2 atmosphere on Earth. So that's actually what happened on Venus. Somehow we pulled it out and got it where it's safe underground. Okay, Mars did not have such luck. We would see it with these rovers. We're boring these holes in and we're looking for what are the rocks, what is the chemistry of the rocks. They've got, these rovers are, can I say it? They're licking the rocks. They're actually poking their fingers into the rocks and they're eating the rocks. They're actually got this mass spectrometers on there, very, very good ones. And what they're discovering is not carbonate rocks. What they're discovering is aqueous rocks, rocks that were formed in the presence of liquid water, but they're not carbonate, they're not limestone rocks. They're sulfate. This is an outcrop that contains the sulfur mineral jarosite, spectroscopically identified without any question. And you see these little blueberries down here that glitter all around and all across the top of that outcropping? This is a black and white close-up of that. Those are called hematites. Those are little minerals that are formed in acid sulfate water. So absolutely chemically characterized. They know exactly what they're looking at. They see this all over the planet, one form of another. This is just one example, these sulfate rocks. So this is a planet not covered with carbonate rocks. It is covered with aqueous rocks, aqueous chemistry. That's what they're talking about when Ashwin was giving his little presentation, talking about all this evidence for liquid water in the ancient Mars. All of these minerals that can only form in the presence of liquid water back when they were formed, a couple of billion years ago, but not carbonate, they're sulfate. So what we're interpreting from that is that we surmise the ancient Mars had less oxygen and less water vapor to remove the SO2 gas, so the SO2 gas stayed. And that led to geochemical differences with Earth that are quite significant. Okay, one of the spacecraft that landed on Mars had one goal in mind. It was Phoenix. Does anyone remember? It was actually a fairly quick spacecraft. It was one of the very first ones that was led by a scientist like me at the University of Arizona. It's called a PI, which stands for Principal Investigator-Led Mission. It's called the Phoenix mission. Does anyone remember? You guys remember the Phoenix mission? It's had one goal in mind, which was to do the same thing a kid would do at the beach. Land, get there, and just start digging. Looking, hopefully, for some volatiles, some ice under the surface. Because as you guys know, we don't get a ton of snow in Louisville. It's not like Cornell or someplace. But we get snow. And you know when that snow gets dirty? I can remember, I was a postdoc at Cornell. I can remember when the snow got dirty, it would just be like June before it started to melt. It just gets that layer of black gunk on top of it, and you stand on it, it feels like tar. I mean, like asphalt. It's really stable. If you put a couple of inches of dirt on top of snow, you're really stable. Well, that's what the idea was. Maybe Mars has a lot of actual volatiles, are not on the surface, but not very far below, just like a handful below. And so Phoenix went down there and did this scrape. So this is in 2008, it's not that long ago. Mars Phoenix dug a trench and found water ice first try. You can see the jumping. I can't do it, but just imagine all the people that at University of Arizona jumping around and high-fiving. There weren't fist bumping back then yet. So on the left here you see it's marked in sols. Remember, a sol is a Mars day, so sol 20. On the right is sol 24. That's 4 Mars days later. I want you to notice a difference. So this was dug on sol 20. The little inset there, there's two-thirds of an inch across. Can you see the little white kind of in a shadow, the little white things. Those are ice cubes, like would fall out of your refrigerator if you're not, your freezer. Those are little ice cubes. See what happened 4 days later? They're gone. They sublimated. Just like the snow on my front lawn when it comes May and finally the snow sublimates. It doesn't actually get runny, does it? It doesn't get liquidy and run, and then sometimes it does, but usually it just sort of disappears. It sort of shrinks. That's going straight from the solid phase to the gas phase. It's called sublimation. And just that happens here in Louisville all the time. But here it is. They didn't get runny. They just disappeared. You can see that same thing down here. There's the ice cubes down here and they're gone over here. A bigger patch that didn't disappear, although it did change. It's just a lot thicker piece. It did change over that. So that was amazing. They said maybe the ice is just barely. I mean, maybe a fairly cheap, only several $100 million instead of $1 billion mission could land, scoop just like a kid at the beach, and it worked. They were like, whoa! And they put some of the dirt into, the rover Phoenix actually ingested some of it, and it clogged. They didn't quite think about how much ice they would have, so they actually ended up making a little mud cake, and they stuck it in the throat of the thing, and it didn't get through to the detector. It clogged. So they had to clear that one out and try another one, and they've learned a ton from that, as you can see, by doing so many missions. Every time there's an opportunity to do a mission, and we learned a great deal from one to the other. So a few days later, some of these ice cubes sublimated. Fascinating. So there is solid water, and by the way, this is spectroscopically confirmed to be water, not something else like dry ice or something like that. Okay, now I want you to look at these couple of craters here. These are actual images. They look pretty, but what they've done is they've taken the spy satellite called the Mars Reconnaissance Orbiter that was mentioned in the other video, the MRO, and it's incredible, literally a spy satellite. It has, I'll show you at the end of this talk, the big punchline is a zoom, 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 4 zooms in to just get to incredibly tight resolution. Well, this is some of those images taken and overlaid into a mosaic and then looked at an oblique angle, so kind of like you were flying around and looking at that. And I want you to notice, can you see that the dirt that's in the crater floor and kind of spilled out, that it's sort of puffed up a little bit? You see, there's what you'd call a little scarp in front there. It's kind of bloated. It's a little softened and bloated. Doesn't quite look like the usual crater pock thing you would see, say, on the moon or in other places on Mars. This really intrigued the imaging scientists, and so they reported it, and then the radar people, the people that use the synthetic radar that are on the orbiters, said, well, we can look for the ice, we can do reflection, and the radar actually is designed to go through the soil and to penetrate about that far, at least. And some of the radar penetrates actually about that far. And if there is ice, it would reflect, and you could actually get radar images of that. I don't have that data, but I have the artist's rendition of exactly what was confirmed. Yes, it's full of ice. If you scrape off about the top 4 inches of the Mars soil, this is what is there today. It's just full of ice. And so it's very stable, and yet still solid. So now let me segue into liquid water. Because we talked about Mars, ancient Mars, 3 billion years ago, having a lot of liquid water, a big ocean at the North Pole. That's great for back then, but it's not like that today. It's a very cold desert today, full of this ice under the surface, but you can't have life live on ice. Life has to have liquid water, and I'm going to tell you why in just a second. Okay, all life as we know it requires a solvent. Now, we are very biased. We have lots of examples of life on this planet. Very live planet, very fertile planet. We have no examples of life on any other body. That's what I was trying to say at the beginning. I spent my entire career working on dead. They're fascinating. I got the winds of Jupiter that go crazy. It's just a lot of fun. But dead as a doorknob. Dead. There's no life anywhere. But on Earth, there's life everywhere. Everywhere that there's even a little bit of liquid water. Like in the ice of the North Pole and the South Pole. If there's just a little bit of liquid water, it's all it takes. And you have what are called, does anyone know what they're called? When you have a life form of bacteria that's really hardy. It's something-ophile. It's an extremophile, and we have a lot of those. What I'm going to show you at the end of this talk is the conditions on Mars that were discovered in 2011 and confirmed to be liquid water just this year. Our extremophiles could live right now on Mars, in the equator during the summer. They could live right now. The conditions, our extremophiles are so hardy, they can actually do it. They can do it. They just need a little bit of liquid water. Why does it have to be liquid? Well, all life as we understand it requires a solvent, and liquid water is by far the most reliable solvent in the universe, in the nature. It has an incredible liquid range. We think of it as 0 Celsius to 100 or 32 Fahrenheit to 212 Fahrenheit from freezing to boiling. That's an enormous range. That's like 3 times the range of most other solvents. What are other solvents? You have them in your garage. Ammonia, various gasolines, things like that. Those guys have liquid ranges, but the liquid range is typically about half to a third the water range. So if you have a planet, you would be making the requirement for habitability that much more stringent because you have to have liquid, and it would be that much harder. Liquid water is just incredible. There's another thing liquid water does. Let me list them for you. So the liquid water temperature range is 2 to 3 times other solvents. When water freezes, it sinks, right? Everything, when it freezes, sinks because it freezes. It gets to be a solid, and it gets denser, and then it sinks, right? Except water. Except water. Water, because it's shaped like Mickey Mouse, with a big oxygen and 2 hydrogen ears, it just quite can't fit it. So it ends up going to about 4% less density right when it freezes. Thank goodness. We would not be here. The fish from long time ago, what would they do in the winter with all that ice forming on the bottom, covering up the plants that they're trying to eat? What would they do? Where would they bury themselves? It would not work. So we have to have not only liquid solvent, it really, really has to be water. That's the second one. There's 4 of these. What's the third one? Water's huge heat capacity.